Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this video lesson, we're going to be continuing looking at numerical integration techniques, and this time we'll be using Simpsons Rule. So Simpsons Rule is based on fitting a parabola between 3 points. So it usually gets a better fit with fewer data points. Okay, but this does require that you're going to have 3 points for one interval. Okay, now what's going to happen is, in fact, we will actually treat each of these as a separate subinterval. So this half and this half as different subintervals. But really, it's because we are fitting all 3 of these points to a single parabola. And then I'll do the same thing with the next set of 3 points, fit those to a parabola. And as we go through and do this, we end up with the area underneath this parabola is going to be approximated by delta x over 3 times the function at the left, the function at the right, and 4 times the function at the midpoint. Now, if you go through and do this, first thing is that you're going to need always to have an even number of subintervals because I need to be able to break these into 2 pieces. Right? So I'll be doing this all the way across. So I have to always have n be an even number. And then I'm going to use this as my formula. As I get through all of the pieces, the endpoints where they touch are going to be used for the left parabolic set and the right parabolic set. So those are going to get doubled, but these in between are being multiplied by 4 because of the rule for calculating the area. And so this becomes my sum. I'm going to need FA and FB, my 2 endpoints, and then for every point in between, I need to determine whether it's an odd point or an even point. If it's odd, I'm going to multiply by 4. If it's even, I'm going to multiply by 2. So this is a little bit different. Let's look at how we could actually apply this. So here is the algorithm. We're going to choose first our number of subintervals, but I have to be sure it's even this time. And then calculate equally spaced subintervals. Evaluate f sub a and f sub b. The easiest way to do this is to take the sum of the odd subintervals and the sum of the even subintervals, and then take this set, multiply by 4, this set, multiply by 2, add your 2 endpoints, multiply by delta x, and divide by 3. Let's apply this to the examples that we looked at in the previous lesson. So the integral of x squared e to the x squared dx from 0 to 1. And I need to open up my Excel, and I have the same files as I had earlier, and we're just going to modify those. So I am going to come down here. I've just copied that, and I am going to name this Simpson. Essentially, I'm going to do the same thing. It's just that I want to first be sure that this is an even number. So I'll just give extra notice in my input box that they need to give me an even number. And now I need to do my formula a little differently. So I still am going to have my f sub a and f sub b, but in between, I want to pick up only the odd terms. And so I can go from 1 to n minus 1, but I want to go every other term. So I'm going to use a step size. I'm going to step by 2. So what this will do is it'll start with 1, and then it'll go to 3, and then it'll go to 5, right? It's going to add 2 every time until it gets to n minus 1. And in this case, then what I'm going to have is really the same formula here, except for that I want multiplied by 4. And that'll add in all of my odd terms. And then I'm going to, I'll do a different counter. It doesn't matter if you use the same one. Just an FYI, but it is somehow mentally more reassuring. This time I want to do the even terms, and so I want to start at 2 and go through n minus 2, again using a step size of 2. I'll need my next, and in between I'm going to now add to whatever I've done so far 2 times my even terms. In this case, I'm going to take delta x over 3 and multiply that times my sum. That should be the only edits I need to do. So if I do this, how many intervals? See, it's telling me it's got to be an even number. So let's do 100. It's a nice even number. And it came up with an answer. Unfortunately, it did not come up with the answer I was expecting. So let me look at this just a moment. I see my mistake. I used j as the counter here, so I need j times delta x. Let's try that again. 100 terms. Okay, now I've got it. So fairly simple. Just make sure that you are multiplying by the same counter as you've used up here. So what about our other example where we had the data set? What do I need to do differently there? Again, I'm going to begin by copying this and using this as my model. All right, so I've made quite a few changes. So let's talk about what I've done here. So I started by reading in my a value and my f sub a. And then I start hopping down through these. Now, the first one is going to be an odd term, and then even, odd, and then I end with my last term. I am going to be going odd, even, and then for the very last 2 pieces, I lose that odd, even pattern. So what I've done is I've done my loop. I'm going to go from I equals 1 to n minus 3. All right, I'm going to do a step size of 2. So within this loop, I'm going to pick up my odd and my even term. The odd term I've called f odd, and I'm going to add that, multiplying it by 4. Then I'm going to go down one more, and I'm going to pick up my even term. I'm going to take that, add it to my sum, but multiply that piece by 2. And then I'm going to jump 2 more jump 2 more for I, and I'll come down here to the 0.914. So it's going to go from here to here to here. But now then, if I do this one and do odd even, I don't want that in the loop. So I stopped my loop at n minus 3. So it's going to stop here, and then I'll do its odd even. That means I have this piece and this piece left. Now you might need to pause and go back through this video again, this little portion here, to make sense of this. But this piece is another odd term. So I stop my loop and I come in and I pick up that last one. So this is f odd last. And so I'm going to add 4 times f odd last to my sum. So that gets this one. And then I need to hop down one more and pick up my f sub b, and then come over here and read b. So that's what I've done here. And then I change my integral to the sum times delta x divided by 3. When I run this, there we go. When I run this, it does get an answer. And it is close to what I had before. I would consider this to be a better answer, because most functions are made out of curves, not straight lines, and so this tends to be a much better answer. So now then we've got a way of doing Simpson's rule and the trapezoid rule for both a function that we can define in a function and using a data set where it will read how many data points. We have one last video in this series, and we're going to look at some of the complications that can occur. Thank you very much for your time.